All right. I'm going to mute everyone as well. There, I just muted everyone, so remember when it's your turn to unmute. Welcome everyone, hi. Welcome to our CalcConf event, focusing on the teaching and learning of definite integrals. I will show you the screen here. This is our table of contents for this issue. The presentations today highlight research that are appearing in this special issue on the topic of the teaching and learning of definite integral. And this is in the International Journal for Research in Undergraduate Mathematics Education. This will be in the June issue. In fact, that will be available. So my name is Rob Ely. Stephen Jones and I are the guest editors of this special issue, which is going to be available on open access for the month of June, we believe. Before we get started on today's presentations, we have a few remarks also from Elena Nardi on behalf of the organizers of the CalcConf series. So I'm going to turn over the floor to her to show you a few things.
Yes, hello everybody. I'm here with you today with my two hats on. One is Ijrumi editor, and I can see at least one of my fellow editors is here, Elise. Hello, Elise. And as a member of the program committee for the Calculus conferences and organizer of what we call the CalcConf 1+5ε event. And this is our very complicated way of saying we have two conferences, conference 1 and conference 2, and we've been organizing, well, we believe really nice events between 1 and 2 to keep everybody engaged and interested in the topic. So I'll have a few slides to share. I can see my fellow organizers, everybody's here. Hi, Tommy, John, Pat, and Alejandro, everybody's here. So let's see where we are with the show slides. I believe this is it. Can you see it now? I believe I'm sharing my screen now, right? Or not yet?
Yeah, that looks great. Thank you.
We can see this.
Brilliant, thank you. So back in 2019, we got together in Kristiansand in Norway. We had a calculus focus conference in upper secondary and beginning university mathematics. It was chaired at the time by Tommy, John, and myself. And quite a few wonderful things that are coming out. Very soon after, not related, closely related, but independently produced, there was a special issue in ZM on calculus learning and teaching around the world, guested by Pat and Gershon. And we actually had our first 1+5 event organized all the way back to June 2021, almost 2 years ago. That was actually followed immediately after the conference by 3 proposals we had actually for special issues that came out between 2022 and today. The proposals came out of teams that worked together during the conference in 2019. So we had our first event in May 2022, the second one in September 2022, and today we're celebrating the third special issue that came out of the conference. So the first one was in teaching mathematics and its applications. It was focused on tools, particularly digital tools to support meaning making in calculus and the calculus education. It was guested by Roger, Anatoly, and Osama. And you can actually find some papers actually around open access on TMA, and you're very welcome to look at that. That was our second event. Our third event followed actually, it was the first special issue in Ijrumi, following from the calculus conference, and Irene, Alejandro, and Alon were the guest editors. Their topic, calculus at the intersection of institutions, disciplines, and communities, in fact, actually became the inspiration for the conference. I will say just a couple of words in the next 2 slides. In the meantime, John Monaghan and other colleagues have been involved with the production of the learning and teaching of calculus with Rob, Post, Marcia, and Mike, and we celebrated the publication of this book in the Rutledge Impact series very recently in March 2023. A lot of events, so that was the 4+, and here we are now celebrating our 5th event. And teaching and learning of definite integrals are very mathematically focused, quite different, especially to the previous one that we had in the Jerome. Very focused on one particular mathematical topic that is so important, especially in transition from school to university mathematics. I would be delighted to work with Rob and Stephen. And we are now happy to say that the issue is in production. It will be ready in the next few days. And Springer has, as Rob mentioned, has agreed to make it available for free at open access through the month of June, which will be great. So we're now days away from the second conference, and this is that's what I mentioned before, that one of our June special issues, the topic that has to do something about calculus being so having purpose and utility and meaning in so many other disciplines. We decided to actually write that theme and actually create and organize the second conference on exactly that. So learning efficient of calculus across disciplines, specifically, and I will mention just a couple of them, a few of them: biology, chemistry, economics, engineering, and physics. And we're asking questions such as, how do these colleagues in these other disciplines understand and use concepts that can be supported or developed in calculus courses? And what does this imply for teaching and learning calculus in these disciplines? We are bringing specialists from these disciplines together with mathematics educators in this conference, and it's happening actually in a few weeks' time. And all I can hope for is that it can be at least as productive and fun as the first conference was. So I think I will stop there, Rob, Stephen. I'll stop sharing.
Can I just say that, Elena, that our plenary speaker in economics is with us tonight, Reiner Voskamp.
And I'm really pleased to hear that you did get the link for the meeting at the very, I think, on the 11th hour. Yes, it's wonderful to have Reiner with us. Right, Rob. Thanks. And Stephen, over to you. I think everybody wants to know what's in the special issue. Thank you so much.
Excellent, thank you. Yes, today we will have a brief presentation from each of the teams of authors of the articles in the special issue. Each one will be about 4 to 5 minutes long, and followed by a couple of minutes for some brief questions. Then we should have some time for further questions after everyone is done, especially if Igor doesn't make it. If you do have a question, it's probably easiest for you to just type it into the chat window if you want. You can, that way we have a running log of them. Otherwise, you can also just raise your hand if you have a question. Okay, so the order of authors is going to be this. So we'll start with Stephen Jones.
Okay, thank you, Rob. Thanks everyone for being here. I'm gonna share my slides, so please let me know if, as I'm going, you're not seeing the slides advancing or anything. So our paper was on quantitative approaches to integrals, and just to kind of jump right in, the research is very clear that we need quantitative meanings for integrals. Area meanings, antiderivative meanings are insufficient kind of on their own for that. Most of the quantitative based work falls under two umbrellas that we call adding up pieces and accumulation from rate. And the purpose of our paper was really to sort of compile, synthesize past work and ongoing work kind of in these paradigms to sort of examine meanings, formalizings, the different foci, reasonings, modeling. And all you can get today is just a tiny little sample of what's all in the paper. We'll focus mostly on the meanings and a little bit of kind of why it might make sense for each of these approaches to have emerged. So let me start with adding up pieces. The adding up pieces idea, kind of paradigm of integrals, follows this three-part structure that matches the Riemann sum pretty closely. The first part, partition, would be exactly what you'd expect. So whatever interval or region or object gets partitioned into very tiny pieces. In adding up pieces, the differential d, whatever, like dx or dt, has a very particular meaning of being a little tiny bit, a little infinitesimal bit. So for example, if this interval was maybe like a time interval, we would chop it up into these little tiny dt pieces. The next thing is the target quantity within each of these pieces. The quantity that you're interested in, a little bit of it exists in association with each of these pieces. So the idea is to say, okay, how do we figure out how much little bit of quantity is in each of these little infinitesimal pieces? A really important thing with adding up pieces, and I think one of its strengths, is that any quantitative relationship is available for sort of getting at that quantity in each of those pieces. So for example, you know, like that second one, if you're doing volumes of revolution, if the interval is partitioned into little dx bits, each dx has an associated disk, and you could say, what I want to know about that disk is its volume, so I can figure out its volume. Or for the third one, if it's arc length, each little piece has a little bit of arc length, and so I can use distance relations to kind of think about that arc length. Or the last one, you know, even into vectors and dot products, it functions the same. We just say over one little tiny piece of the path, this quantitative relationship in the dot product gives me a little bit of work. Then the last one, sum, is a kind of what you'd expect it to be, is we have little bits of this quantity in each of those pieces. And so the integral, the meaning of the integral is a summation, a special summation of the quantity over all those little pieces. So in this case, the integral symbol means sum, the way that Leibniz originally intended when he introduced this symbol. And so all of these integrals mean adding up those little bits. So again, like that second integral, you're adding up the little bits of area for each of those pieces, or for the third one, you're adding up little arc lengths for each of those pieces. Okay, so to switch and kind of do the same thing with accumulation from rate, to sort of talk about it. We sort of also saw kind of a three-part structure in accumulation from rate, but a different structure, so different kind of meanings entailed here. The idea with rate function is there's two quantities you're interested in that dynamically covary with each other. And that there's a rate function that's going to quantify that covariation for every moment. A really important thing then in this paradigm is it's important to realize that all integrals must be rate-based. So if there's a different quantitative structure going on in a situation, it has to first be kind of converted into a rate structure before it makes sense to talk about integrals for it. For bits of variation, there's sort of an open domain. So there's a starting point A, and then it kind of continues on open-endedly, which is partitioned into delta x's. And then as the quantity x progresses into a delta x interval, there's a new quantity called dx that is defined, that ranges from the left endpoint of the delta x and then kind of continuously and smoothly grows within that delta x. So in this case, as x entered into that second delta x, it would be growing, that dx would be growing from the left endpoint. And then the idea is that f varies by r times dx within each delta x piece. So there are delta x's and dx's kind of happening simultaneously here. So then in the first, and then in the third structure, part of the structure, the accumulation is as x increases from A, you're going to kind of track the open-ended variation in f. A couple of points, though, is that to distinguish x as a location from the x as it was used in kind of those previous two parts, you have to switch that previous x to a different symbol. So for example, t. So rx dx becomes rt dt. And then you also then need to make the delta x's infinitesimally small for the accumulation function to be exact. So delta x is infinitesimally small, as well as the infinitesimal dx ranging kind of inside that delta x to then construct an integral. So let me just finish a little bit with just sort of like where these two paradigms emerge from, what were kind of the purpose of these two paradigms. So for accumulation from rate, so Thomson and Dreyfus said the fundamental theorem of calculus frames our entire course, and that's really the motivation in this kind of a thing. So there's this real intimate connection between rate and amount, and accumulation from rate exclusively focuses on rate and dynamic covariation. So if the fundamental theorem of calculus is the central goal, then this approach makes sense. And we kind of call this an intramathematical coherence, because the coherence is focused on kind of within mathematics, the concepts connecting together. So what would be the purpose behind AUP? The idea here is that integration in its own right is a really crucial STEM concept. It has some advantages in that it's very flexible with the kind of quantitative structures you can use. And if you look across science education literature, this actually matches very, very closely to how scientists think of integrals. And so if STEM usage is your central goal, then adding up pieces is a really attractive paradigm for that. And we call this kind of an interdisciplinary coherence Again, kind of trying to connect across disciplines rather than just sort of within. And one note, and Brindley will talk about this in here, is that obviously the fundamental theorem of calculus is still within an adding up pieces paradigm. It's not like it's not part of it. It's just not the central goal in that case. So with that, thank you. And whatever time there is left in that little mini presentation, if anyone has any questions. Kevin, it looks like you're raising your hand.
So I was wondering if you could comment on the extent, how well these frameworks extend beyond single variable calculus.
Good question. So I'll say a couple of these things. In fact, I had a slide kind of almost ready for just some of those kinds of things. So a couple of these are sort of single variable. Some of these are multivariable or line integral type things. The really adding up pieces continues to function exactly the same. So like, for example, the upper right integral over here, if you're thinking of that, this is a three-dimensional object and it works the same. You partition it into little tiny dv pieces. That density rho sort of applied across one of those little tiny volumes gives you a little bit of mass. And then the integral symbol means add up those masses across the three-dimensional object. So it functions a lot the same. Same thing with the line integral. That path C gets partitioned into little tiny dr bits. That dot product within each bit gives you the amount of work over that little bit. The integral sums those little bits of work. So adding up pieces, I think, coheres pretty well with that. Accumulation from rate obviously can extend to these things as well. When Rob and I have worked with people who use this paradigm and we were trying to make sense of these, it did feel like as you got to the more advanced ones, it became quite a bit more elaborate and required several kind of additional constructs to work. And again, I'm not saying that as in like it doesn't work, it does. In our kind of understanding of it, we do feel like adding up pieces functions a lot the same. Accumulation from rate does kind of get progressively more elaborate as you work through those, as far as conceptual understanding, right? Rob, did you want to add anything to that?
No, I think I want to respond also to the question that Aaron Wangberg put in the chat just briefly, if you don't mind, Stephen.
Yeah, go for it. Absolutely. Yep.
The question is that position velocity relationship seems obvious using AUP. Is this relationship as evident when working with the other approach, the accumulation approach? I would say it certainly is. In fact, it's not just evident. I think it's sort of central to the other approach. The fundamental issue of accumulation is the way of is the idea of getting students to understand something like a position as an accumulation of velocity over time. So I mean, I'm not. It would be nice to sort of draw this a little bit as well, but I would say that that's absolutely central to the accumulation approach, and that, in my understanding, that image actually becomes almost a central image that is metaphorically extended to other kinds of images or of situations where the rate is maybe a little bit more difficult to immediately imagine. I think we should hold off on other questions for now for this paper until the end, just to make sure that we don't run out of time. So let's switch over now to the paper by Ortman and Simmons.
Okay, hi everybody. First, let me thank Rob and Stephen for organizing all of this and putting in a lot of work over the past several years. I'll be talking about some work with my colleague Courtney Simmons. We were looking at productive reasoning, primarily quantitative reasoning that was required of students as they engaged in modeling with definite integrals. And let me just start by giving you a chance to look at this slide. This presents the final stages of work of two students that were working together, Matt and Julia, on the problem that's stated at the top. So look at what they wrote at the end of their work and just kind of take away whatever you might from that. And then we'll go into some of our analysis of this kind of situation. Okay, so these sorts of answers were what primarily prompted us to think about models that we could use to understand how students were reasoning and how they were putting together their own definite integrals and models using definite integrals for various phenomena. We called our approach emergent quantitative models, drawing on the idea of emergent phenomena as represented, for example, in the work on quantitative reasoning and in RME with the emergent models heuristic, and also from Bruce Sharon's work on symbolic forms. The idea being that we're going to be talking a little bit about categories of meanings that we'll call local, basic, and global models, but primarily the ways in which these meanings develop are through complex interactions between those different things. And that's all kind of drawn from similar phenomena appearing in a lot of this prior work. So for us, a basic model is what students will primarily think about when they approach a situation. For example, distance is velocity times time, where for any corresponding set of corresponding quantities, those individual values can be considered constant. For example, distance equals velocity times time. A local model is when students, for example, try to apply that kind of reasoning in a definite integral situation, say, for example, where velocity is varying, and they can't consider velocity constant over any given amount of time, but they can develop a local way of reasoning about that in which velocity may be considered to be approximately constant. And then their global model refers to the meanings that they bring to bear on these quantities as they start to pull all of these together, say in some sort of an accumulation. So that gives you just kind of a basic definition of what we mean by these types of basic local and global models. The driver of the way that we see these things developing is in the emergence that happens in the interaction between these various models. And so there's a lot of complexity in what that looks like. And I can't obviously in a few minutes talk to you about every aspect of this, but I'll be bringing out a few different of these categories as we come back to this example. So here you can see that these two students were both thinking about what we would call the same basic model, which is either energy is force times distance, can be thought of as some kind of a multiplicative model in that sense, or perhaps in this sense, maybe the students were thinking more in terms of energy is mass times gravity times distance. But so as they were working with each other, they were invoking that same basic model, but that played out in two different, what we call local models. And you can see that laid out here. For example, the distances that they were imagining moving were very different. So for example, Julia was imagining moving the chain by small DH amounts repeatedly, while Matt was thinking about moving different amounts of chain large distances. And then we can kind of see what that looks like. So here's what Julia was imagining, partitioning the chain into segments and moving each of those segments up to the top, one at a time. All right, so for her, the delta H referred to a small length of chain segment, and H was the distance that she was imagining those segments moving. So she developed her model, right, applied locally to each of those little bits. That's how her definite integral emerged. Matt, on the other hand, was imagining moving the entire remaining amount of chain one small segment at a time. So for Matt, the amount of distance that was being moved each time was an amount delta H meters. And then the force was represented by 9.8 times 15 minus 15 over 10H, right? That's the was the amount of mass remaining in the chain for each one of those motions. So they both came up with slightly different definite integrals, reflecting the different quantitative meanings that they brought to bear in those local instantiations of the same basic model. And I think that's all I have time to kind of elaborate for now, but be happy to get comments or questions.
Thank you, Michael. Anyone have any questions?
Could I ask you, and I know you don't have time to like elaborate on all this, but I'm really curious. In the local model, you have lots of these different types of bits.
Mhm.
And I think Archimedean and infinitesimal, I think I know what you mean by those. Riemann product, I assume I probably know what you mean. Curious, like trivial, generalized, what do those mean? And maybe even Archimedean,
Okay.
if you have a few seconds.
Yeah, so sure. I mean, these are just refer to different ways that students might be thinking about a local model. So for example, we call the trivial model what you might think of an integral, say, Q equals the integral of dq. So the trivial model refers to where the differential form is just representing a small amount of whatever the integral will be accumulating. An Archimedean versus an infinitesimal model refers to the students thinking about small but non-infinitesimal amounts of change or increments in quantities. Whereas in infinitesimal model, the students might be thinking about something smaller than any real numerical value. The Riemann product, I'll just kind of maybe finish on that. For example, Julia's local model is something that we would call a local Riemann product. And this is what's kind of necessary. For example, if you go back to Stephen's talk, when they were talking about converting something into a kind of a rate model, right? Julia could do that, right? She could eventually kind of think about maybe this, the integrand, right? The 9.8 times the mass quantity in parentheses here as perhaps a rate. And think about the integral that way, right? Where, and that's kind of the typical Riemann sum structure, right? Think of the integral as a limit of sums of a function times delta H quantities. That Matt's not going to be able to think about, at least in this quantitative interpretation, a rate in that same way, right? For him, the DH is embedded in, right, this density times length piece here in terms of the mass, and then the other components of a gravitational constant and distance come into play out there. So he wouldn't even really want to write the DH kind of out on the end of the integral because of that. So we would call that not a typical Riemann product structure.
Okay, I think we'll hold on to, oh, sorry, Stephen. Go ahead. Well, I think we'll hold on to any other questions, again, just for the sake of making sure we don't run out of time. So if you think of any other questions or follow-ups that you want, just hold on to those until the end. And in the meanwhile, we'll turn it over to Vicky and colleagues. Vicky, you are muted. There you go.
I couldn't unmute myself. There we go. All right, give me 1 second here to try to get this to open up right. I don't know why it is not. Well, if you have to, there we go. All right, so we are going to be talking about student understanding of negative definite integrals in math and physics. And we're going to spend a lot of time talking about what we're going to call backward integrals, where the integral is taken from 7 to 2 instead of from 2 to 7. So we had 2 studies that we did for this paper. The first one started with a written survey on lots of different negative integrals, not just backward integrals, and follow-up interviews with some of those students. They had a lot of graphical representations with physics context, and those students were either concurrently enrolled in a second semester physics course or had completed it the previous semester. And what we found from that first study was that backward integrals were particularly difficult for students to make sense of if the quantity was negative or why the quantity was negative. So we did a second study, clinical interviews with a handful of students that were specifically about backward integrals. And we wanted them to justify why the backward integral was negative, or if they knew that the backward integral was negative. We had them look at it symbolically, graphically in terms of area under a curve, and within a physical context of stretching a spring or releasing the spring. We had a range of students. I won't go into that depth right now with my 5 minutes. So for our data, all of the students in the second study did know that the backward integral was negative compared to the forward integral. And the students nicely described integrals in terms of both area and adding up pieces in these ways that we would want them to do. For the fundamental theorem of calculus, so a lot of them, they looked at a general expression of the integral and also a specific problem. So we gave them the integral from a to b of f of x dx and said, what do you know about this? What can you tell us about this? And then we gave them the integral from b to a of f of x dx. And they could nicely use the fundamental theorem of calculus to tell us that one would be positive and one would be negative. Same with a specific problem. They could compute that. They could tell us that one would be negative and one would be positive because of the order of subtraction. So then we asked them to talk to us about why that relationship holds when we're talking about area under the curve. And that one caused some issues with sense making, we'll say, for those students. Though some students said, well, it's the same area, whether you add it from left to right or from right to left. Some knew that it should be one should be positive and one should be negative, but couldn't justify why that might be in terms of area. And some talked about just direction kind of on top of or outside of the integral, if you will, that if I go this direction, one's positive and one's negative, but couldn't really break it into the pieces that we wanted. 2 students recognized really quickly that if I was taking the integral, the backward integral, I would have a positive height for the function we gave them, and the width would be negative. We gave them a context problem as well, the energy to stretch or release a spring. And for many students, this gave them a reason to consider delta x as the signed quantity. Kind of made, oh, delta x would be negative here or positive here, depending on which direction we're stretching it. But what we kind of wanted to know was, can they think about, or do they think about dx as a signed quantity? So this is jumping to the end of the paper here with a lot of things being skipped right now. But near the end of the interview, we specifically said, can dx be negative? And here are a couple of student responses. So Sarah says, well, no, I don't think dx would ever be negative because it's just a distance. And she described it, whether it's on this side of the positive x values or even negative x values, we're still talking about a distance, which is a positive quantity. Matt was one that was just like, he knew something should be negative and couldn't figure out what until the very end of the interview. And he says, that's probably the hidden spot I couldn't figure out before. Yeah, I would say that this dx in the backward integral would be negative, and this one in the forward integral would be positive. I also want to note he was really comfortable earlier on in the interview talking about delta x having a sign, but had never thought about dx as having a sign or not. Anna was another one early on in her interview. She was one of the ones that described delta x as a negative width, but when asked at the end of her interview if dx could ever be negative, she says, I've actually never thought of that, so I'm not sure. I mean, I guess it could, but I just always viewed the dx as the indication of what term to integrate to. So I'm not actually sure, I guess. So our key takeaway is that in physics, it's really necessary to consider the delta x and probably even the dx. If John were giving this talk, I think he would say definitely the dx. I'm not sure. I won't put words in your mouth, John. But to consider at least delta x, probably dx as a signed quantity. And I think we should give our calculus students more opportunities to work with those types of problems that have them explore those ideas where delta x being negative makes sense. I think that's it. Thank you all very much. Devian.
Did the notion of arc length or absolute value arise at any point in these conversations?
John, you're on here. Did that come up in the surveys at all with arc length? It certainly did not in the second study.
I don't think arc length, no. I thought maybe in the second one, though, there was some absolute value things where people were thinking about, but I can't remember now. I don't think so, actually, now that you say that.
I don't think so. Oh, and Pat.
There's a question in the chat from Pat Thompson. Oh, I'm sorry, did I interrupt?
No, I was just looking at that. So
okay, yeah. So did any students give a hint that when thinking delta x less than 0, that they were thinking of accumulating from B to A?
Yeah, I think so. And I'd have to look back at the data. It's been a little while. But there was certainly a couple of these ideas. One was this kind of like global view of direction. So I'm going from B to A. I'm taking away pieces, if you will. But others were a little more computational of like, well, it's B minus A over N, but now it's A minus B over N. So looking at it a little bit more symbolically in that case, or x2 minus x1 versus x1 minus x2. Does that answer your question, Pat?
Yeah, thank you.
Mm-hmm.
We also have a question from Tommy Dreyfus.
You mentioned AUP at the beginning, Vicky. You didn't mention AR, and I wonder, when you think about accumulation from rate, then you think more dynamically. And when you think dynamically, then this dx becomes more naturally negative, at least to me.
When you think about it as a rate, it becomes more?
Not because of the rate. The rate's positive, and if you say have an area, but the dx moves, I think, should do this, moves from right to left. The thing becomes dynamic. So I think that might be a way to bring in the negativity.
That could be. Yeah, I have to think about that. To be honest, I think about adding up pieces much more than I think about the AR perspective. So I think that's just a little, it's something I want to explore. I want to think about. That's an interesting idea.
Okay, well, same idea here. If you've got any other thoughts, hold on to them and we'll save a little time at the end. By the way, there's not, I don't have to run away at the end, so we can let this run on as long as anyone else wants to after our sort of official time is over. In the meanwhile, let us turn this over to Dre and Manogue.
All right. So welcome everybody, and thanks especially to Rob and Stephen for sponsoring the special issue and encouraging our work. Let me back up and show you the title slide. So this is a paper that written by Corinne and myself, attempting to explore some differences between the way vector line integrals are taught in mathematics and physics. Our basic tool is something called a representational transformation diagram, which was introduced by Rabindra Bhattacharya and discussed on Bhattacharya, Amy, and Minogue a couple years ago, which is essentially a flow chart that represents a concept image, and it's particularly used when the concept image is rich. And the idea is to connect the pieces of the concept image in a flow chart, diagramming the connections. And then we classified, or I should say, they classified, and RTD classifies the connections as a bit depending on the number of arrows connecting the different boxes. And you'll see an example on the next slide. But the distinction is between translation, where you're just rewording things, rephrasing things, consolidation, where several concepts are combining into a single one, and dissociation, where you're using a starting point and fanning out into consequences. We use the length and the complexity of an RTD as a proxy for the cognitive load involved in mastering this concept. And the things we look for are in particular what we call an iconic expression, which tries to summarize the core of the concept, how the iconic expressions are unpacked, and what is the starting point for calculation. Corinne is reminding me in chat that the various connections are time ordered, and that you're looking to see what is happening when someone is solving a problem. Okay, the iconic expression, as I said, is trying to be the symbolic representation in the simplest form. And so we look for geometric representations that are easy to remember and that contain instructions for unpacking. So what we did is we examined a couple of standard textbooks. This one is from Briggs Cochrane, a standard calculus textbook, trying to diagram the way line integrals, vector line integrals, are presented in the textbook. And if you start in the middle, I shouldn't do that. The iconic expression is the one over here, f dot TDS, and a lot of effort goes into trying to derive that formulation of what a vector line integral is in terms of previously introduced quantities. It's then unpacked into the one I was trying to start with, because it's the one I tend to think of as most basic, which is what we would call the starting point for calculation. And what's very interesting in this textbook, and we're using that as a proxy for quote unquote all standard or most standard mathematics calculus textbooks, is that a lot of effort goes into deriving the form f dot TDS. But when students are asked to solve problems, they're never starting up there. They're always starting from f dot r prime dt. And then you can proceed down to further unpack that into the pieces used in an actual calculation. We looked at, I believe it was John Coley, one of the standard texts that introduces similar concepts in physics. And here the pieces are somewhat different. There's more of a bring in one idea at a time to gradually evolve from a notion of work as a simple product of force times distance up to work as a line integral, as the canonical model for a line integral. And again, down here, where my mouse is, next, a second line from the bottom, would be the iconic expression. But in this case, it's also the starting point for computation, that you both derive that viewpoint starting from work and then use it when solving problems. So I don't have time to go through the full details of this analysis, but I hope you can see just by a quick look at these two pictures that the path is different, the paths are different, and the cognitive load is significantly different. Thanks to the editors, we were encouraged to include our own proposed learning trajectory as to how we would go about teaching these concepts ourselves. And so that also appears in the paper. We have a version of adding up pieces that we call chop, multiply, add. And this final slide, which I'll leave you with, is an attempt to show how that notion smoothly generalizes starting from initially functions through densities up to vector line integrals with very little changing except the actual pieces, but the conceptual notion of how you're integrating as chop, multiply, and add is uniform throughout. The very bottom then shows the branching off into physics applications, which are for the physics side, the goal of introducing line integrals. I will stop there.
Thanks, Tevin. Any questions?
So I see a question in chat from Mike about f.tds versus f.dr. The question is whether you think of f.tds as a dot product followed by a scalar integral, or as the dot product of a quantity such as a force with a vector infinitesimal. There's two ways to put in the parentheses, they're not equivalent. And we're trying to make that distinction. In the mathematics iconic expression, we would argue f.tds is very much being reduced to a scalar line integral. So Pat has a question about chop, multiply, add. One of the reasons we like chop, multiply, add is that we are inevitably chopping space. That our vision of chop, multiply, add is you're chopping the domain. Something like electric charge requires multiplying. That's where the multiply piece is. Some sort of density, a charge density, with some sort of chopping up space, a length, an area, or a volume. And one of the reasons we like to stick in that multiply piece explicitly is so that you can envision chopping up the domain, usually space, then multiplying a density, then adding up.
A quick follow-up question about charge density.
Yes, but I wouldn't know how to use it in an accumulation of rate sense in higher dimensions, if that's where you're trying to go with it. I think perhaps that's a conversation we should.
Can I jump in? Like, no, charge density is not a rate of change. It's like charge density is how much charge is in this little piece divided by the size of the little piece. If you introduce charge density as a rate of change, it completely discombobulates a physicist's brain.
And as we know, we don't want that to happen.
No.
Let's hold on for any more questions about this again until the end and turn this over to, thank you again, turn this over to Brinley and Stephen.
Okay, let's share my screen. Okay, are we seeing it? I'm hoping it's okay. I got thumbs up. Okay, so I'm Brinley Stevens. I worked on this out of Brigham Young University with Stephen, like Rob was saying, and our paper is on learning integrals based on adding up pieces across a unit on integration. So just a little bit of background. Obviously, there's a lot of work on snapshots of integrals and understanding them quantitatively. We've already seen a lot here so far, but and this list is not exhaustive in any way. But basically we felt that there is a gap of how a student goes from the very, very beginning of learning integrals all the way up until the fundamental theorem of calculus without touching on that through an adding up pieces perspective. So that's what we set out to do. Our framework went through a lot of iterations, but it was heavily influenced by Vicky Seeley's work and Von Korff and Rebello, Swedon and Yerushalmi's frameworks. And Stephen already talked about some of them, but we kind of felt that there was this level 0 to it where they had to orient just to the basic quantities before they could really reason quantitatively. But then, as Stephen talked about, there's a partitioning of the domain to get a target quantity using a local model, like Michael Ortman and Courtney Simmons were talking about, adding up those target quantities. Where we extend from what Stephen talked about is varying that upper bound so that students can imagine adding more partition pieces and extending that upper bound throughout the length of your domain. And then to imagine the output of that new extension, and then to be able to reason about a function relationship between the input bound and the output quantity. And then each of these can be represented graphically, numerically, and symbolically. There's a table in our paper that goes into that like in great detail, but for time reasons, I won't be doing that. So the activities that we had students do, we had 3 pairs of students in an interview setting. And these were the contexts and the lessons that we kind of went through with the students. So in lesson 1, we began with this fuel pipe context of fuel going through a pipe, first at a constant rate. Then we gave them a table of values, and they had to think about how much accumulated fuel there was in the time frame. We specifically held off from a graphical representation in the early stages due to our piloting studies. We found that if graphs were introduced too soon, students often abandoned some quantitative meanings, so we held off there a little bit. And then in lesson 2, we introduced what we call the road context, where we're leveling out a terrain and we want to know how much dirt's on hand. And this is where we could introduce the graphical context representation, as well as seeing how students thought about negative function values, because the fuel pipe didn't have that. And it gave them a chance to kind of consolidate their thinking. Then at the very end of lesson 2, we introduced a volume context. This one didn't require as much time, but we wanted to give a final check so we could assess their understanding, so they could bring it together, but also so that they could experience integration with a non-rate example, so they could think about tiny slivers of volume being added up. Then in lesson 3, we returned to the fuel context to add in that graphical representation, but we also extended that upper bound to think about as time incrementally continues, how is that going to affect the amount of fuel in the tank? Then for lesson 4, we went back to the road context, but we thought about extending that upper bound, and then we thought about extending the volume context as well. So that's kind of the outline of how the lessons went. So by the end of interview 4, this is what the road context looked like with that extension. And students were able to reason quantitatively about thinking about these little pieces of dirt that they would scoop up and put off on the side. And so they were thinking, okay, I'm adding a little bit more, oh, a lot more in this one. And then they started reasoning about losing dirt as they filled in the pit. So here are some of the graphs that they were able to roughly sketch using their quantitative meanings for the context. So we were really pleased with their work there. And then, although this wasn't meant to cover the fundamental theorem of calculus, it was meant to prepare them for that next step that they would be taking in their class. And it was exciting to see the connections they were starting to make at the end. So we pulled some quotes from students that were just kind of fun. So Alice said, you know, this one, is the derivative of our function. So this function here is the derivative of this function. That's so cool. Oh my gosh. And they were so excited that they could take ownership of that. And obviously they didn't have these ideas formalized yet, and they weren't able to bring those together into the actual theorem, but they were definitely ready. And as Brian said, it means that the value of our initial graph is kind of providing the instantaneous slopes of our graph right here. So again, he's seeing this connection between the two graphs and how those could potentially be related. So in our next steps, that would be a great thing to look at, is how they're ready for fundamental theorem of calculus using adding up pieces. And that is my last slide.
Okay, any questions for Brinley? I'm hoping that you are seeing that our authors are much better experts on integrals than they are on how long 4 to 5 minutes is. So we're running so bit late. If people need to run away, of course, obviously you can. We have 2 more people. We've got Igor showed up. That's delightful. And then we have Nilsson and Knudsen also after this as well. So maybe since I don't see any questions right now, let's move on to Igor Kantorovich, who's meeting us from very, very early morning in New Zealand.
Hi, good morning, everyone. Good evening, whatever you're having right now. Let me talk to you a bit about a particular type of problems that my colleagues who have been teaching calculus for many years drew my attention to. So hopefully this is something that is quite familiar for you as well, when students are provided with some sort of a function and asked to find the area between the curve, let's say x-axis, over some interval. So one of the things that my colleagues told me is that this is actually one of the tricky questions that students get, which is quite surprising. The question could be treated quite procedurally. So I delved into questions of this sort, and one of the things that I noticed, that first of all, when we ask about areas, there are at least 2 approaches that could be taken about that. So if we look at the Mathematics Encyclopedia by Weisten, he talks about integral area and defining it practically as something that people call net signed area or signed area, which is an integral area. The approach that I'm more familiar with, that when we are provided with questions of this sort, at least in the mathematics courses, the intention is for students to find a surface area, which is the area of the surface or the amount of material needed to cover it completely. So for example, in this case, when the function crosses the x-axis, the 2 approaches to area, they clash. And I had one of the most fascinating communications with the reviewer in this paper, who was probably coming not from mathematics studies, but from studies of physics or something like that, who insisted that in these questions, it's way more reasonable to treat area in a surface, in an integral way. But we will talk about that as a surface area, as something which is intended. There are research findings that talk about students' confusions in this case, and one of the common ways that have been documented is that students apply a single integral as a model or a tool to find the area. So in this case, it would be something like that. So I call this way of thinking as a SEMA. And it's absolutely valuable as long as the function keeps its sign. But it was interesting for me to find out how widespread this way of thinking, this SEMA, is on students' completion of an instructional sequence. And it was also interesting to delve into the details of this way of thinking and what happens when we zoom in into the smaller parts of the actual students' actions that they take when they approach the problems of this sort in this way. I turned to a first semester service course in mathematics in my university. Students mostly majored there in statistics, business, economics, and commerce. And I had access to two data corpuses. One, this is a typical problem in this course that is often given at the final exam. So I was lucky to have access to nearly 12,000 answers of students in 17 multiple choice final exams over a decade. And one of the distractors was always consistent with this SEMA way of thinking about areas. And my colleagues offered a new video assignment to students where students were asked to generate a video, a short one, where they explain a solution to a problem or to several problems from a particular bank that they constructed. And one of the problems was relevant to this area calculation. This is something that students did at home. Here are a few of the findings from this type of work. So first of all, if we look, hopefully you can see my my arrow. We looked at the final exams, and overall we see that in questions of this type, the expected answer, the surface area, the answer was offered by less than 50% of the students, when the option which was consistent with the SEMA way of thinking was chosen almost in 1/3 of the cases. In most cases, this was the most common, the most popular distractor. And there were semesters when the SEMA options were chosen more commonly than the expected one. Another thing that we did, we tried to have a look whether it is important what kind of function is actually involved in the questions of this sort. And the bottom line is that it does not seem to make such a big difference. So the students' preference for the SEMA way of thinking ranges between 20% and 38%, but we could not find clear patterns in this regard. The fact that students are choosing this type of answers in a final exam, of course, does not mean that this is actually how they think. So this is why we turn to the video solutions that they recorded at home while having access to their friends, online resources, textbooks, assignment, and all sorts of things. So what was actually interesting for me, first of all, that even when all these resources were accessible, still out of 190 students who chose relevant problems to solve as their homework assignment, the expected answers when they were showing their solution path was provided only by 90, when 100 still adhered to the SEMA approach. And when we delved into the nuances of what they were actually doing and how they were approaching stuff, so maybe I will not exhaust you with this figure, but what turned out is that there is no single way in which they think about that, but we were able to identify different stations along this network, something that we call the figure network, something which is based on the figures and what does the curve look, what is the area look, and the integral network. And in each of these stations, there is a potential for different sorts of confusions when they try to apply SEMA. So this is the qualitative part of this work that actually shows what students can do in this regard. Rob, how I'm doing with time?
We should probably move on. Since we're a little bit over now, is it okay to?
Yeah, absolutely. Thank you so much.
All right. Well, thanks very much, Igor. This massive data set is amazing. Maybe we'll just hold on for questions. I want to make sure that we don't run out of time for our last pair of authors. And we're almost then at the end, and we'll have some questions, kind of open the floor for everyone then, okay? I think you're still muted.
Can you see my presentation?
Oh, it looks great. Yes, thank you.
So if I do it like this, is it in full screen now?
Yes, that's right. Good.
Good. The title of our paper is First Year Engineering Students, Interpretations of Differentials and Definite Integrals. And I have written this together with Christopher Hägglund-Knudsen, which is also participating here. The background, it's actually a master study conducted by Christopher, where I was a supervisor, where he focused on upper secondary students' interpretation of integrals and found that a lot of the students, almost everyone, interpreted as just actions to be carried out or antiderivative or area under the curve. And none of the students actually emphasizes the sum aspects. So we were wondering if that was the case also for engineering students, where we know that engineering students later on in their program has to deal with integrals understood as sums in some way or another. So a research question was about what characterized the first year university engineering students' interpretation of the symbols involved in the fundamental theory of calculus. And the project was funded by Matric, which is led here from the University of Agder, where we belong. So just to give you some small background on how integration is presented in the students' calculus textbook. And this is what we choose to denote as a rigorous limit-based approach, where typically an example is given and it's defined a lower sum and an upper bound sum of Riemann sums, and the integral is and the limit is taken, and the integral is defined as the sandwich between these lower and upper bound sums. So it's a purely limit-based introduction that dominates the introduction chapter of integration. And we did this study by interviewing 15 volunteer engineering students in their first year, and they were all displayed with this fundamental theorem of calculus as displayed in their textbook from Adam and Essex. So they were asked rather openly to give an interpretation of what this means, but we also went into details and asked about the different symbols, for example, the differentials and the integral signs. Our theoretical background, just very briefly, is rooted in symbol interactionism and social constructivist perspective, where we actually emphasize interpretation and the student's meaning making. Also draw on Duval and Steinbrink. To give you some few examples from our data, we found that a lot of the students use the language which we associated with more infinitesimal approach than a limit-based approach. And this came about by expressions like bars with very, very small widths. And if you make a lot of them and sum them up, you will find the integral under the curve. So this dominated the students' explanations, but they were all kind of or a lot of them had this sum-based interpretation, but not much in terms of limits, even though that dominates the textbook. We saw actually some examples of what could be associated to limit-based approach in their explanations. For example, some emphasize the upper part and the lower part, and something between there is defined as the integral, but when we went deeper into the conversation with this, it soon shifted towards kind of bars and widths and this terminology more associated with infinitesimal approaches. could mention a lot of sub results that came about there, but due to time limitation, I will skip that. But I will just briefly show you how we use the Steinbringer's epistemological triangle to see something about how they developed their reasoning. And it was based in the sum of bars, and then these sums became the reference context for these bars being infinite small. And then a lot of students got problems because what happens when they have no width anymore? And they didn't separate between approaching zero and becoming zero, or some didn't. And that was a difficulty for some of the students. And we ended up with trying to categorize these 15 students' explanation into different categories. And as you can see from the overview here, a lot of them were having interpretation that could relate to infinitesimals, and only 2 were defined as having to do with limit-based interpretation, even though that was the introduction both in teaching and in the textbook. So to summarize the findings, we saw that most of the interpretations that the students were offering through their conversation could be linked to infinitesimals and width of bars and so forth. And since these students are engineering students, these explanation also have a great potential as we see it, because they will need some based applications later on, and to have a kind of infinitesimal approaches to how they regard, or in their terminology, might be fruitful to build on to more meet these needs. Thank you.
Thank you, Hans Christian. Does anyone have any questions for these authors? And I think at this point, we can also just have questions in general for everyone here. And again, fly away if you need to. The video will be made available somewhere. Thanks again to everyone for pitching in. Tommy Dreyfus has a question.
Well, I think there's been a discussion going on in the chat, which I haven't followed, but I was fascinated by Corin's emphatic no to Pat's question whether the charge density or mass density or whatever couldn't be interpreted as a rate. I think if Pat had asked the same question about velocity, it wouldn't have generated such an emphatic no. I mean, Corin, you probably wouldn't have said, no, this is not a rate, this is how much path the body did in a certain time interval. So where is the difference? Now, if you've discussed all this in the chat, maybe we should go somewhere else.
Corinne's no longer here. I would have to say that I also don't really see how to interpret charge density as a rate. But I think her point was more that it's not a productive point of view for upper division physics.
And one thing maybe I'll add to that, also, just to summarize a couple of things that I was putting in the chat, is that, like, is it possible to construe some of these as rates? Like, sure, but I think sort of the contention that Tevian and Corinne are making is that that's not how a physicist would think about it. And like, one of the questions is sort of why force it to be a rate when that's not how a scientist is conceptualizing that quantity. And it, I think in an adding up pieces, there are lots of contexts that are rates, right? There's a lot, shows up a lot, but there are contexts where even though it could be construed as a rate, like Tevin is saying, that might not be the most productive scientific way of viewing that quantity. And so, why force it into that other construction as opposed to kind of a broader view of integrals that can allow all these different quantitative structures to be on equal footing and to function one just as well as the other, kind of a thing. So I don't think it's a matter of can it be, but like, does it make sense to want to do that? Would you agree with that, Tevin?
I would very much, and I think you phrased it very nicely and very diplomatically.
So
I'll
the question
concur.
I have.
Sorry,
Yeah.
go ahead.
So the reason I said that is because, and this might reflect the difference between an expert and a novice, but when students are learning the idea of density of anything, they're taught it as if it's an attribute of an object, not as if it is something that is invariant under variation. So the idea of density, say, just the simple density of mass per unit volume. If it's taught and students learn it in a way that it's a property of an object and not something where the volume can vary, or you can think about filling a volume, then if you think of it as filling a volume with a mass, then thinking of it that way, it becomes a rate of change. So it really depends on whether you're thinking of ideas like density as a property of an object or as some sort of generalized invariance. To get it as a generalized invariance, it pretty much has to be a rate.
Right. I think I was typing in, and I don't know if I remember actually finished typing it, that like we think of it as a property of an object first, I think, at least on our side of things. And then you can think of it as a rate. I don't disagree that you can, but I think we don't conceptualize it that way when we're working with it until much later, I guess. But yeah, because I was saying we start with like a whole object and break it down to the little bits and how much mass is in each little bit. Usually that way, as opposed to starting from a little bit and adding up at first, right? And so maybe that's why that distinction is made. I haven't thought through that all the way, but.
So if you, and that's why I said that what Stephen said might be an expression of a cultural phenomenon rather than an epistemological phenomenon.
Right. It's not, neither of those is incorrect or inappropriate. It's just situational. Maybe.
But there's more than correctness that's relevant. At issue is what is best for which students and which disciplines, and is there actually a tension there? And I'm not saying I have any answers to those questions.
And at what moment in their learning?
I don't disagree.
Other questions or thoughts you find folks have? I'll give you a sec to think of it, but in the meanwhile, if there's anything that the organizers want to mention or put on anyone's radar, go for it.
Well, I think it's worth mentioning that the very kinds of issues that we've just been talking about with regard to intensive quantities, the conference in Bergen is designed specifically to bring these kinds of issues to the front.
Yeah, this is a great point. It's hard to imagine a more lovely place to be in in June also. So go to Bergen, everyone. Okay, well, again, I'm happy to stick around as long as anyone wants, if you have any other thoughts. Otherwise, it's good to see you all. Thank you again for coming, and thanks to all the authors for their great work.
Rob, thank you very much to you and Igor and Irene, to the editors and to the authors. I really enjoyed reading this special issue.
Thank you very much. Great.